Okay, so now we're going to take a moment to describe a second new set of numbers. Okay, these are called the complex numbers. Complex numbers, don't get worried, that does not mean complicated numbers. It's not really any more difficult than the imaginary numbers at all. In fact, I think they're a little more straightforward as long as you understand the imaginary numbers already. Complex here, if you ever heard of like a sports complex or a shopping complex, a shopping mall could be called a shopping complex. Complex just means a lot of little things brought together into a big thing. So complex numbers are numbers where two different number systems have been brought together into one. So the two different number systems would be our real numbers we're used to and our new imaginary numbers. If we want to put those number sets together, we get a complex number. Okay, so a complex number is any number that can be written in the form a plus bi, where a and b are real numbers and I is the imaginary unit. In these complex numbers, a is called the real part and b is called the imaginary part. So once again, we have two parts, the real part and the imaginary part of our complex numbers. Okay, we're going to take a moment to review what we know about number systems in general. So there are things called natural numbers, things called whole numbers, things called integers, irrationals, and rationals. These are all what we call the real number set. So everything in here is a real number as opposed to being an imaginary number. Sorry, looking for my pen here. There we go. So all of these are part of the real numbers. Okay. Originally, when people use numbers, we only use things like 1, 2, 3, so on and so forth. It took Indian mathematicians some time to create the whole number set, which includes the number 0. So for example, when people were originally counting, you could point to rocks and say there's 1 rock, that looks like 2 rocks, that looks like 3 rocks, but nobody pointed to the dirt and said, right over there is 0 rocks. Nobody said that initially. However, over time, people found that that was actually a useful concept to have, that 0, to keep track of no number. Okay. Beyond that, when people were talking about math problems, if you wrote a problem that said, for example, what is 5 minus 6? Let's put it in real terms, 5 apples minus 6 apples. Well, if you ask somebody that, if I have 5 apples and I take away 6 of them, how many do I have left? They would say 0. What do you mean? How am I going to take away 6 apples from 5 apples? Well, with the introduction of the negative numbers, we have a way to describe that through math symbols. We can say that 5 minus 6 is -1. We can think of that as like I owe somebody an apple, I'm in debt, however you want to conceptualize what that negative really means. But that then defines what we call the integer sets. Integers go from -infinity to +infinity, where they're all whole numbers without any decimals there. An irrational number is a number that does not end. A very famous one would be pi. So pi starts out 3.14, 15. It is very close to 22 divided by 7, but it does not equal 22 over 7. Okay, 22 over 7 would be a rational number. This would be something that has some definite end to it, like 1/2, 0.5. That's a rational number. An irrational number is this one that just keeps going and going and going. Okay, so those are all of our real numbers. If we look at a Venn diagram, then that kind of puts all of these numbers together into one picture. The picture you'll see is this. So let's focus here just in this rectangle that says real numbers for start. So the real numbers includes the rational numbers and the irrational numbers. So the irrational numbers, like I was saying before, includes things like pi. The rationals includes things like 1/2. The integers includes numbers like -1. The whole numbers includes numbers like 0. And the natural numbers is just that 1, 2, 3 that we're used to. Okay, so whole numbers include natural numbers, integers include whole and natural numbers, rational numbers include integers, whole numbers, and natural numbers, and real numbers includes both the rational and the irrational numbers. Okay, if we want to go one step past that, we can say the biggest category we could ever describe is the complex numbers. The complex numbers include real numbers and imaginary numbers in them. So, for example, if b in your complex number is 0 and we just don't have anything here, then we're dealing with real numbers. But if b does not equal 0, if we've got some amount of imaginary parts in our complex number, then we are dealing with an imaginary number. Now, if we want to talk about a pure imaginary number, then it would be when a is 0, when we don't have anything here and it's just some amount of imaginary numbers. Okay. So two complex numbers are equal if and only if their real parts are equal and their imaginary parts are equal. The commutative and associative properties of multiplication and addition and the distributive property hold true for complex numbers. So to remind you of those, if you're not familiar, the commutative property for addition and multiplication just means that you can add in any order. A plus B is the same as B plus A. 3 plus 5 is the same as 5 plus 3. Multiplication-wise, A times B is the same as B times A. It doesn't matter. That is commutative property. The associative property means that if you have a string of multiplications, for example, it doesn't matter which order you do. 5 times 4 times 2 is the same as 5 times 4 times 2. I would look at that visually with like a volume. So if I wanted the volume of this prism, it's going to be the height, the length times the width times the height. But you could just as easily do the height times the length first, then times the width, or the width times the height first, and then times the length. Doesn't matter what order. Okay, so these properties, property that it doesn't matter what order you multiply, and that we can kind of flip these equations over and they still mean the same thing. Those are still true for complex numbers. That's what this first paragraph is telling us. To add or subtract complex numbers, we're going to combine like terms. So we're going to combine our real portion with our real portion and our imaginary portion with our imaginary portion. Right here, that is combine the real parts and combine the imaginary parts. Two complex numbers of the form a plus bi and a minus bi are called complex conjugates. The product of complex conjugates is always a real number. And I will give you just a real quick example of that. So here, if we have a plus bi and a minus bi in our square diagram here, we get a squared, we get two terms that cancel out in these corners, and we get negative b squared I squared. Two b's came together, two i's came together, negative out front. Okay, so a plus bi times its complex conjugate, a minus bi, gives us a squared minus b squared I squared. The I squared is equal to -1, which turns that negative sign into a positive sign. Okay, so a squared and b squared, well, a and b are both real numbers, so when we add them together, we get a real number. These complex numbers multiplied by their complex conjugates give us real numbers. So just to try to summarize that again, if you have a negative number, you can break that down into its square roots, which are imaginary numbers. So an imaginary number times an imaginary number gives you a negative number. A complex number times a complex number, that is the complex conjugate, will give you a real number. So we're saying that we can break negative numbers down into imaginary numbers, and we can break down any real number into complex numbers. Okay, moving on. A radical expression is in simplest form if no radicand contain fractions and no radicals appear in the denominator of a fraction. So this is just what we call conventions. Conventionally, this is how we like to have them written. It doesn't mean that if you wrote it in a form where you had a radical in the denominator that the math wouldn't work. It's just that there's a certain way that we try to rearrange things to call it the simplified form. Okay, just like 50 over 100 is perfectly fine to write down, but we'd rather simplify it to 1 over 2. They're both perfectly fine to write, but one of them is the conventionally simpler one. Okay, similarly, a complex number is in its simplest form if no imaginary numbers appear in the denominator of a fraction. You can use complex conjugates to simplify a fraction with a complex number in the denominator. This process is called rationalizing the denominator, and we'll see that in an example that's coming up.